So today we're talking about Kepler's three laws of motion. Do you guys know who Johann Kepler was? Anyone? No?
I'm guessing he was a scientist.
He was a scientist, right? Anyone ever heard the name before? Raise your hand.
I've heard.
Yeah, you heard the name before. Probably don't know what he did. He came up with three laws of planetary motion, and he actually, an interesting story. I think, and I'm a little fuzzy on my history here, but I believe that Kepler was a student of a guy by the name of Tycho Brahe, or I'm butchering that name. It's a Dutch name. Does anyone know that name? Tycho Brahe, Brahe, something. Anyway, whatever it is. This Brahe guy he basically lived in an observatory for years and years and years, and all he did was make observations and write them down. So he'd be like, okay, Venus, azimuth, elevation, time. Venus, azimuth, elevation, time. He'd do this every single day for as long as he could, for years and years and years. He'd end up with just volumes and volumes of books of data. And didn't really do much with it. It was kind of an overwhelming thing for him, I think. It's like he knew where things were with respect to his observatory, and that was it. Kepler actually came along and got the idea that he had all this data, somebody's got to go through this data and kind of make sense of it. So that's what Kepler did. He went through years and years and years of history of planetary motion, Jupiter, Mars, Venus, the moon, the ones that we could observe, and stars as well. And Kepler actually tried to figure out what the relationship was, how planets were moving around the sun. All right, and you guys know what he figured out?
They weren't they weren't perfect circles.
Right, exactly. He looked at the stuff. The first thing he realizes is it couldn't be perfect circles because things just weren't quite right. What else did he figure out? Right, if they weren't weren't perfect circles, what were they? Ellipses. He figured out the best thing that would fit his observations, or the tables and tables, the books and books of observations, was that it had to be an ellipse. All right? And moreover, an ellipse where the sun was at one of the foci. Do you guys know how the mathematical definition of ellipse? I know these two guys do. What's an ellipse? Yeah.
A series of points drawn around two foci.
The locus of all points that are... Yeah, you got it.
Yeah.
Yeah, the locus of all points that are what? Raghav, go. You had to know this last year, right?
Equidistant from...
No, not equidistant.
The sum or
The
equidistant.
sum,
Yeah,
right.
The sum
Sum of the distance from any point on the ellipse, the sum of the distance from that point to the two foci is always constant. And you can do the whole ellipse with a string thing. Do you guys know what I'm talking about?
Bill Nye did that.
Yeah, okay. Bill Nye did it. Did anyone actually do this in like math class?
Yeah.
You put the two push pins in and tie a string to them?
Yeah.
Remember?
I remember that.
And
yeah.
the string is always the same length, right? Because it doesn't stretch, but it does move around, and you can draw out the ellipse with the string. All right, so yeah, anyway, so the sun is always at one focus, and what's at the other focus? Right, nothing. Good. So yeah, sun's at one of the foci. All right, moreover, he figures something else out. I need a volunteer. Come on up. Normally you're gonna play the part of the sun. And I'm gonna play the part of a planet going around the sun. All right, ready? So here's how a planet moves around the sun. Ready? What do you notice?
It speeds up when it's closer to me.
Speeds up, goes fast when you're close, goes slow when you're far, right? And all right, go have a seat. Nice job.
No.
All right.
Sorry.
Uh,
I understand.
nice job, Neural. Yeah, so he figured out that planets go fast when they're close and slow when they're far away. And moreover, there's actually some math to it. If you were to describe a sector, do you guys know what a sector is? Of like a slice of pie is a sector? The sector, the area of the sector drawn out over the course of 24 hours of a planet going around the sun is always the same. So if you think about that, when the planet is close, the radius is small. It does a sector that looks something like this, where it goes from here to here with a big angle. And then if the planet is over here, it only goes from here to here, because this radius is big, therefore the arc length is small, such that this long skinny sector has the same area of this short fat sector. Does that make sense? All right, and that's another way of saying you go fast when you're close and slow when you're far.
It's a specific relationship.
It is it's a specific relationship, right? Okay. And then lastly, he figured out if planets were all in circular orbits, which they're not, but they're really close to circular, there's a relationship between the amount of time it takes to go around and how far away they are. So what do you think it is? If you're farther away, how much time does it take, more or less?
More.
It takes longer. Which has a longer year? Jupiter or Earth?
Jupiter.
Jupiter. Why?
Because it has a much larger orbit.
Much larger radius. Right. And that relationship is t squared is proportional to r cubed for the sun, for every planet that goes around the sun. So if you wanna, oh boy, let's pick some numbers that actually work here. If you quadruple the period, in order to quadruple the period, you need 8 times the radius. Wait, is that right? Yes, that's right. 9 times the period would be 27 times the radius. All right, okay. It doesn't depend on the size of the planet at all. If you could have a big planet and a small planet at the same radius, they're going to have the same period. And we talked about that one before, I think, didn't we? Did we mention that? How screwed up it would be if you're doing a spacewalk and because your mass was less than the space station, you would orbit slower? How messed up would that be? It would mean you couldn't do spacewalks. Because the second you left the space station, it would be going faster than you, and you'd be screwed. Right? So the size of the object, the mass of the object doesn't really matter. All that matters is how far away it is from the thing it's orbiting. Good? All right. Now, here's the thing. Brahe took the data, Kepler analyzed the data, and came up with laws. But what didn't Kepler do? Prove them. He didn't explain why. All Kepler came up with were some laws. But Kepler didn't have the mathematical background to come up with a theory. Who was the one who finally mathematically proved that these 3 things should be true? Newton. And actually that's what in the first few chapters of, if you read Principia, that's the first few chapters of Principia, was explaining Kepler's laws. Good? All right. So what we're going to do is we're going to talk through Newton's explanation of Kepler's laws of planetary motion. And what were the 3 laws again? Elliptical paths with the sun at a focus, equal areas in equal times, and t squared is proportional to r cubed. So we can do all 3 of those using Newton's laws. You ready? Here we go. All right. So
What's the relationship between, is there a specific number with
how he figured what out. T squared and r cubed. He just did it based on, he knew how long it took to orbit, and he also knew how far the planets were away from the sun.
Do we know the constant?
He didn't have to know a constant in order to do it. All that he had to do was compare Jupiter and Earth and Mars. And he know Earth has a certain radius from the sun, from the center of the sun, and it has a 365-day period, right? And then he knew Mars had a bigger radius from the sun and had a bigger period. And he also knew that Jupiter had an even bigger radius from the sun and an even bigger period. But he figured out for Earth, Mars, Jupiter, and Venus, this relationship always held true.
Do we know what the constant is that
What?
relates it?
He didn't.
Do we?
We do. And that's what we're going to do with Newton's laws. All right, so here we go. First one, elliptical paths. I can't do the whole proof of ellipses, but do you guys know the simpler case of ellipse? What is an ellipse that's even simpler than an ellipse? Circle, right. So we're going to do it for a circle. If you want to do the proof for the actual ellipse, you're going to have to read through Principia, but it's several pages long. And I do have a copy downstairs if you want to take a look, but it's whatever. It's kind of mind-numbing. Yeah, but it's a lot of triangles that he drew. So anyway, here we go. Newton's proof of Kepler's law. We're going to skip the ellipse part. We're just going to do it with a circle. So if you're going in a circle, why are you going in a circle? Well, what's the name of the force? Gravity, right. Now, if gravity is the name of the force, Newton knew that gravity was gmm over r squared, right? Now, and he also knew that that force would equal the mass times the acceleration, right? So, the force equals the mass times the acceleration. The force always points towards the center, right? And so he did a little bit of math magic, and he said gmm over r squared equals mv squared over r, which should sound familiar, right? Which m cancels out? Mass of
the body.
the body that's moving. It's called a planet. So you're left with mass of the sun, and you get the velocity equals square root of gm over r if you have a circular orbit. Agree? What's big G? Gravitational constant. What's m?
Mass of the sun.
Mass of the sun. What's r?
The distance between sun and planet.
Distance from the planet from the sun, between the sun and the planet, right? So, are any of those variable? No, not if it's going in a circle. G is always a constant. Mass of the sun we're assuming is a constant. And if it's going in a circle, r is a constant as well. Wouldn't you agree? So all of those things are constant. So what's true about the speed? It's constant. And you get uniform circular motion according to Newton's second law. Does that make sense? So that's the proof of uniform circular motion if it's a perfectly circular orbit. And like I said, if you want to prove it for an elliptical orbit, you can. It's a lot more work than I showed here. Sound good? All right. We're going to do number 3 next, the period squared and the radius cubed. So, all right. So if you've got something going around in a perfect circle, speed, what's the definition of speed? Speed is distance over time, but that's circumference over time, which is 2 pi r over period for a circle, right? Speed is 2 pi r over period. But we know from right before that the speed is square root of gm over r. So that means 2 pi over period is equal to square root of gm over r. Agree? You do a little math magic, and what you end up with is t squared equals a whole bunch of constants times r cubed. Does that answer your question? All right. And that's what it is mathematically. It's 4 pi squared over gm. And you'd need to know what the value of g is and what the value of the mass of the sun is in order to use this. Good? All right, cool. Yeah, so the period doesn't depend on the mass of the planet. It only depends on the mass of the sun and the distance, and g. But g is a constant, just like pi. All right, next up. Last one. Equal areas and equal times, or goes faster when you're closer and slower when you're farther. This one is a little bit tricky. I'm sorry for the picture. It's a little hard to follow here, but what we have here is we've got the sun in the center, and this is the planet moving from time 1 to time 2, from here to here. Now, I know that it's actually going to curve along that path, but we're going to take a little tiny slice over which the arc is essentially a straight line. Is that okay? All right, so here we go. The distance traveled is called delta S. The radius is called r. All right. Now, what's the equation for the area of a triangle? 1/2 base times height. Well, if r is your base, height would be delta S sine theta. Agree? So height would be delta S sine theta. So the equation of, the area of that triangle would be 1/2 r delta S sine theta. Sound good? Now the thing is, delta S, that's a distance traveled, right? Wouldn't that be a velocity times a time? Or speed times a time? So you'd have 1/2 RV sine theta times the time it took. Wait, RV sine theta, doesn't that sound familiar-ish from some unit? RV sine theta. When have you done something that sounded like RV sine theta? Momentum. What kind of momentum?
One person here and then the object.
Yeah, an object flying by and you have to turn your head, right? What kind of momentum was that? That's angular momentum. Yeah, linear momentum is just m times v. Angular momentum is mRv sine theta. Of a particle, right? But we are talking about a particle because it's a planet that's moving. So, instead of just writing RV sine theta, let's write mRv sine theta and then divide by m. So in other words, you get 1/2 mRv sine theta times t, all divided by m. Sorry, I jumped ahead. I'm going to pull this time, divide by time, so I get area per time equals 1/2 RV sine theta. Area per time is how quickly you're sweeping out area, right? That's the area created in 1 day, or in 1 hour, or in 1 second swept out, right? Area per second is 1/2 RV sine theta. But RV sine theta is the same thing as writing mRV sine theta divided by 2m. And mRV sine theta is L, angular momentum. So, oops, that's supposed to be a 2 there, sorry. So the area per time is equal to L over 2m. L over 2m. Is m constant? Is the mass of the planet constant as it goes? Yes. Is L constant? Is the angular momentum of the planet constant as it goes around in this ellipse? Yes or no? You sure?
No.
Is there any torque on it from the gravity? Let's see. So here we go. When it's right here, What direction is the force? Is there any force on it?
Yes.
What direction is the force point?
Towards the
Toward the sun. What direction is the r vector?
The same direction.
Actually, away from the sun. So the force is that way, and the radius vector is that way. What's that angle? 180 degrees. What's the torque? Zero. So as the planet travels around the sun, there's no torque on it from the gravity. Because there's no torque on it from the gravity, its angular momentum must be constant. Wouldn't you agree? And if the angular momentum L is constant, and the mass is constant, what else must be constant?
Delta U.
Yeah. The area swept out per time must be constant. So we say, so Newton actually proved this law, Kepler's law, by saying that the angular momentum of the planets is constant, and therefore the area must be equal for a given amount of time. Does that sound right? All right, cool. So this has a habit of showing up on multiple choice. By the way, all of these show up on multiple choice. This one shows up, you know, something to the effect of the fact that equal areas are swept out in equal times are expression of which concept? And the answer is what? Conservation of angular momentum. Right? Since there's no torque on it, the area has to be equal. Good, good? All right, moving on. Let's talk about, we'll move away from all this Newton stuff. Let's talk about energy real quick. Orbit energy. Okay. Let's say Normal's headphones are the sun, and you've got a planet going in a big ellipse around the sun. No, sorry. When's the planet going the fastest? When the radius is the smallest, when it's closest, right? So when's the kinetic energy the most?
When the radius is smallest.
When the radius is smallest. Good. Well, let's talk about potential energy, though. When is the potential energy the most?
When the radius is greatest.
When the radius is greatest. How come? Aha! Because Jordan says that potential energy is negative GMM over R, right? So if you have a big R, that means you have the least negative, right? Or the other way of thinking about it, if kinetic energy is the least out here, then potential energy has to be the most. Or the other way of thinking about it is the way you've always thought about it, which is potential energy is the most when you're the farthest away from the planet, right? Right? You lift an object up, it's farther away from the center of the Earth. That means it has more potential energy. Good? So all these things agree with each other. All right, so when's the potential energy the least?
When the K is the greatest.
When the K is the greatest, right, when it's closest. Good. All right, let's talk about circular orbits. We're done with ellipses for a second. We'll go back to circular. Do you guys remember way back when, 3 weeks ago before break, we talked about the potential energy of a planet is negative GMM over R. Wait, R squared or R? Negative GMM over R. The potential energy. Could we come up with an equation for the kinetic energy of a planet? What if it was going in a circle? What's the equation for kinetic energy? 1/2 mv squared. But do we know what v is? If it's going in a circle, what's v? square root of G M over R. So what's 1/2 mv squared then? It's 1/2 m
Squared
gm
Over R.
over R, or gmm over 2R. That's interesting. The potential energy is negative gmm over R always. And if it's going in a perfectly circular orbit, the kinetic energy is gmm over 2R. Is there more potential energy or more kinetic energy if you're in a circular orbit at a given radius? Which is bigger, the kinetic or the potential? Hint, the kinetic is over 2R, and the potential is only over R. Potential is more significant. Potential energy is more significant in a circular orbit. Now, here's the kicker. Potential energy is always negative. And what about kinetic energy? Is kinetic energy negative? Why not?
Because you can't have a negative velocity.
Well, you can have a negative velocity.
It's squared.
Velocity squared can't be negative. So kinetic energy is a smaller positive number, and potential energy is always a bigger negative number, which means, what's the total energy? Negative. A negative number. Some negative number. That's interesting. If you're in a circular orbit, the total energy is negative. All right? So here we go. The total energy is the potential and the kinetic energy, which is basically just 1/2 of the potential energy, because the kinetic is half the size of the potential. Does that make sense? All right. Now, for a circular orbit, we can create a graph, and you're going to know and love these graphs. You're going to see these again and again in both this unit and again in electrostatics and again in magnetism. What we have here is a graph of potential energy in blue, kinetic energy in red, and total energy in purple. You guys see it? If you are at a radius of R, your kinetic energy is positive, but your potential energy is at a bigger negative. So when you add this big negative potential to this smaller positive, you get a total energy that's still negative. What happens if you go further away from the planet? What happens to your total energy? It increases. It increases. Your kinetic energy drops, though. That's interesting. What happens to your orbital velocity as you get further away from the planet? The speed at which you're traveling. Or you go further away from the sun. What happens to your speed? It slows down. But what happens to your total energy? It increases. How can you decrease your speed but increase your total energy? How is that physically possible? You're in a new orbit that's farther out. You're moving slower, but you actually have more total energy now. How is that possible? You're farther from the sun. The potential is more important than the kinetic. Does that make sense? All right. So, if you want to go to an orbit that's further out in space, will you fall into a farther orbit, or will you fall into a nearer orbit naturally? Or the other way of looking at it, if you want to get to a higher orbit, do you have to expend fuel or do you gain energy? Let me give you a real-life example. In 2005, December 23rd, we launched the satellite UFO-11 for the Navy. All right? We started out in a relatively close-in orbit, and we wanted to go out to a geosynchronous orbit, which is way, way further out. Did we have to expend fuel to get there? Why? What's the total energy further out, more or less?
More.
Why is it more? Because aren't you traveling slower?
They're getting more potential energy.
Because the potential, you're gaining potential energy, and that's greater contribution to your total energy than the kinetic, loss of kinetic. Does that make sense? All right, cool. All right, geosynchronous orbit, I think we already talked about this. This was in your homework over the break. A really high orbit where one orbital revolution perfectly matches the period of Earth's rotation, which is 24 hours. 24 hours is 86,400 seconds. You do the math, and you're all going to have to do this math if you haven't done so already on your homework. You get GMM over R squared equals M4 pi squared R over T squared, and you get a radius of 42,000 kilometers. But you need to take in, a lot of times they ask about altitude, not radius from the center of the Earth. What's the difference between the altitude of a satellite and the radius of its orbit?
Altitude from the surface.
Altitude is from the surface, so you have to subtract the radius of the Earth. All right? And if you do that, it comes out to be 35,900 kilometers for the altitude, or about 22,000 miles up. You guys know the radius of Earth in miles, approximately? Like, how many miles is it from here to China, for example? Or India? It's kind of on the opposite side. Anyone ever get on an airplane and go there? Right. Took forever, right? How many miles was that? Don't know? Don't know how many air miles you got for it?
My dad deals with that. I just sit in the plane.
All right, yeah, it's forever because it's about 12,000 miles. Earth's circumference is about 24,000 miles, so the radius, or the diameter is about 8,000, or the radius is about 4,000 miles. So the radius of Earth is about equivalent to going from, Florida to Nome, Alaska. That's about the radius of Earth.
Near Anchorage.
It's past Anchorage. Yeah. Yeah, it's way out near Russia.
Oh. It's like
So.
near the tail.
Yeah.
Okay.
Yeah. So anyway, so that's actually it might be closer to Anchorage. Might not be. Yeah. Anyway, that's a ballpark about the radius of Earth. All right. So anyway, that's all I have.